Space, or memory, is another resource that gets consumed by programs as they execute. And so it's something that you need to worry about. Now, the consumption of space is taken up by values. So a long list takes up more space than a short list. But it also gets taken up by frames. So you need to know how many frames exist because of different function calls in your program at the same time. And this will involve some new concepts. So the new concepts we need to keep track of are which environment frames do we need to keep around during evaluation, and which ones can we just let go. So here's the story. At any moment, there's a set of what are called active environments. And values and frames in those active environments consume memory, or space. Any memory that is used for other values and frames, not in an active environment, can be recycled. And the Python interpreter does this automatically by reclaiming the space that it used before when it knows that that information is no longer needed. So, which are these active environments? Well, an active environment is for any function call currently being evaluated, meaning we called it, but it hasn't returned yet. There's another case, much less common, which is a parent environment of a function that exists in an active environment. So this situation occurs when you've defined a function within another function, and so its parent frame is not the global frame, but some other frame. As long as you need that function, you also need its parent frame and all of the other frames in its parent environment. So, fortunately, Python Tutor can visualize which frames are active for us. Here's our definition of fib, which computes Fibonacci number 6, and there's a setting, which I'll show you, that says don't display exited functions. So in this way, it will actually delete the frames of anything that has already returned. So when we call fib6, obviously it hasn't returned yet because we have some work to do. And that's going to involve calling fib4, which has to complete before we ever try to finish fib6. And fib4 involves calling fib2. And so all of these are active frames at the same time. fib2 calls fib0. fib0 actually returns. And once it returns, it's no longer active. And so it's just going to disappear. And in its stead, we have replaced it with a frame for fib1. So notice, we had f1 and f2 and f3. We created f4, but then got rid of it because we didn't need it anymore. And now we're up to f5. So if we continue this process, we'll see that once fib4 was done computing fib2, the fib2 frame was removed. And now we have the fib3 frame, which is the other part of computing fib4. So that goes on for a while, and eventually the fib4 frame is gone entirely, and we only have the original f1 frame because we're not finished computing fib6, and we have the f11 frame that was created for computing fib5. That does some work, eventually that gets deleted, and fib6 can finally return the value of 8, and then there's no more work to do. In our code, we can also see how many frames are being used. So let's define a higher order function called countFrames, which takes in some f and defines a counted version, which takes some argument n. What it's going to do is increment the open frame count. It's also going to keep track of the maximum number of open frames at any time. So if the open count is actually larger than the max count, we can change the max count to be the open count. Now we'll get the return value by calling f on n. Now it's time to close this frame, which just means subtracting 1 from the open count. And then we can return the result. The open count starts out at 0. The max count starts out at 0. and we can return the counted function. So if we define fib really quick, we already know that it makes many, many recursive calls. But what we don't know is how many frames are open at any given time, or what the maximum number of open frames is. So we can figure that out by calling count frames on fib, and calling fib on some number such as 20. So it's computed the 20th Fibonacci number, and fib.openCount should be 0 because we've returned from every call to fib that we've made. But the max count will tell us the maximum number of frames that were open at one time. And the answer is 20. So that's an indication of how much space is used by this function. It doesn't need to open 6,000 frames at a time, only a few. Now, how can we understand why the number came out 20? Well, here's the tree-shaped process that we use to compute fib5. And let's say we've done all this work already, we still have to do all this work, and we're about to return from this call to fib1. Well, we can figure out which calls have an active environment. It's this one, this one, this one, and this one, which haven't returned yet. The ones over on the left have already been called and returned, so any memory used by these frames can be reclaimed. And then over here, these haven't been called yet, and so we don't need to worry about that. So the maximum count of frames open is the longest chain you can find in this tree, which in this case goes from fib5 to 4 to 3 to 2 to 1, is length 5.